Well, good afternoon. It's 12:16 on Monday, the 12th of October, 2020. It's supposed to be Math 227 Calculus 3 class. The trouble is, right now I'm the only one showing up. Now, I should have maybe done this before I got started, but I think I'll do it now. I'm going to see if I can pull up and make sure that I did the I can't see it on the screen. Oh, here we come. Kira's here. All right. Kira's here. So far, the only one here. So let's go back to this slide. Kira, any questions, issues, concerns, problems before we get started today? All right, you're the only one here so far. I was just beginning to worry that maybe I didn't send the invite properly or post it or whatever, but since you're here, I know that it did go out correctly. And if you don't have any issues or concerns or questions, we'll go on and get started where we left off. Oh, here comes Miguel or Jesus. Okay. All right. So Jesus is here, or Miguel. Okay. And Kira is also here. I was just saying that, do you have any questions, issues, problems, concerns, anything? Jesus. I take that to be a no because I can't hear anything. I hope you can hear me. Can you? Okay, it looks like, say again? Okay, I know you can. I was just wondering, it sounds like Jesus says he connected the audio, but I can't get an indication that he's able to hear me yet. But anyway, if you don't have any issues or problems, we're in chapter 11, Vectors and the Geometry of Space. In 11.1, the first section, Vectors in the Plane. And we've done, we're on page 757, just getting to talk about standard unit vectors, which I'm going to make a big assumption that all of you are familiar with. So both of you are familiar with, and all that may be listening at home as well, because you probably had enough physics so far, you know what we're talking about with standard unit vectors, and maybe in previous math classes as well. So here's where we go, and again it's page 757, and I can't get the PowerPoint to advance. Okay, there it goes. In the plane now, we're still dealing in the plane, only two-dimensional space here. And in those two-dimensional space, the unit vectors are, the standard unit vectors are 1, 0, going in the positive x direction, and 0, 1 going in the positive y direction. Standard unit vectors in the plane, and they're denoted by little I, bold little I is 1, 0, and bold little j is 0, 1. Now, I don't write bold, so therefore if I'm writing these, here's how now this is an old habit of mine, but I like it because it reminds me that I'm dealing with a unit vector, and also hopefully will remind you as well. I will write this as I like this and j like this. I put the caret symbol over a unit vector, okay? Whereas a regular old vector, I'm going to put just an arrow, but I'll put the housetop over a unit vector. Not just I and j and k, later we'll get to k, You know those are unit vectors, but I still do it. But when you get to other unit vectors that are not the standard unit vectors, I'll still do that to remind myself this is a unit vector. And in the plane, this is how they look. I is 1 unit from the origin in the positive x direction. J is 1 unit from the origin in the positive y direction. So 1, 0, 0, 1. I hope y'all are familiar with that, right? Okay. And those vectors can be used to represent any vector uniquely this way. Now remember, this notation I always called component notation. Its vector v is angle bracket, meaning it's a vector. The v1 is the component in the x direction, v2 the component in the y direction. Okay? Now, you could break that down into v1, 0. That would just be the component in the x direction, plus v2, 0, v2, that would be just the component in the y direction. Or, remember now the v's here, this v is a vector. These are scalar numbers. These are just quantities, numbers. You could pull the v1 out and say v1 times 1, 0 and v2 times 0, 1. Well, 1, 0 is the I unit vector, 0, 1 is the J unit vector. Now back when I was growing up with vectors, this is what I considered component notation, because they didn't have the angle bracket notation back then that I ever saw, okay, or remember one. This was what I would have said was component form. And it is. The horizontal component times the I vector plus the magnitude of the vertical component times the J vector. That was component form. However, this is what I now call IJ form. In other words, using your standard unit vectors. So the vector V is equal to VII, V1I plus V2J is called a linear combination of the unit vectors I and J. That is a scalar number, and that's a scalar number, and it's a linear combination of those two. The scalars V1 and V2 are called the horizontal and vertical components of V, which are also the components here. I mean, that's what they were before. They still are the same components. It's just now we pulled them out of the vector notation and are introducing them in front of the standard unit vectors. Okay. So here's example 5, middle of page 757. Let u be the vector with initial point, and this is a point, notice the parentheses, 2, -5, terminal point, -1, 3. Let v equal 2i minus j. Write each vector, okay, that's u and v, as a linear combination of I and j. Okay, so here we're going to do A. A is going to be u. So vector u, oops, sorry. I drug my pen and then I wrote it wrong. Okay, here's vector u, not a unit vector, just a regular old vector u. Okay, write that vector as a linear combination of I and j. Okay, so what would that be? Okay, now it's going a couple steps back. Now, I don't know how you like to do it. In my mind, it's easier to write it in component notation first. Okay, so in component notation, that would be, if I can find my pen again, where is it? There you are. It's always terminal minus initial, so that would be a -1, -2, comma. I'll put them in parentheses if that's. Oh, here comes Laurent. Okay, hold on just a moment. Hang on to that thought. I'll be right back when I finish marking Laron present. Okay, the bottom part of the alphabet is doubled number of people who are in the top part of the alphabet. Poor old Kira's hanging that down by herself. Then the bottom part of the alphabet is here in great strength. So good, Laron, you're here. We're on we're in chapter 11, vectors in the geometry of space, in section 11.1, vectors in the plane, that's two-dimensional space, and we're now talking about standard unit vectors, doing example 5 on page 757, just about the middle of the page. Okay, now here was our problem. Here is, let u be the vector with initial point 2, -5, terminal point -1, 3. Notice these are points because they're in parentheses. They name them as points. So the vector u would then be always its terminal minus initial. So it would be, if I could find my pen here, where is it? There it is. -1 minus a 2, that's where we were there, comma, and then terminal minus initial 3 minus a -5. That's the y component. Okay, what does that turn out being? It means it's the vector -3, 8. Okay, now once you get it in component notation here, it's a piece of cake to write it in a linear combination of I and j. That would just be -3i plus 8j. You just use these components as the coefficients of your unit vectors, standard unit vectors. Now that we have it in that form, we can do w, which w is equal to 2u minus 3v. That would be 2 times, and let's just go on and write it in this form, -3i plus 8j okay, minus 3 times your v was given up here as 2i minus j. And Laron, you just come in. I was saying I always try to represent unit vectors with the housetop. That has a name and I've already forgotten what it is. I was calling it before, but that thing, just to remind myself, but also just got into a habit of doing that. So what do we do here? Well, we can distribute the 2 across the parentheses, and that would give you -6i plus 16j minus 6i again plus 3j, distributing the -3 across, and then combine like unit vectors. Okay, that would be -12i and plus 18j. Alright, let's see how the book did. They got -3i plus 8j, good for them, and -12i, oh, plus 19. I can't add, can I? Okay. I don't know why I missed that one. Okay. And none of you corrected me. What are y'all doing? Just sitting there, huh? It's plus 16 plus 3 is plus 19j. And that is indeed what the book got. Good for them. Alright, now that's how I did the problem. Let's see how they do. I'm going to erase any questions before I erase this? How I got anything on here? Okay. Then let me erase that ink and let's see how they proceed. So U is, just like we did, they actually named it Q1 minus P1. That's the terminal first component minus the coordinate of the points. Now these are coordinates of the point. Q1 minus P1 comma Q2 minus P2. They chose to do it in component notation as well. To me, that's the easiest way to go. Then plugging in the numbers, that was a -1 minus a 2, excuse me, comma 3 minus a -5, and that gives you -3 comma 8. And then writing that in as a linear combination of I and j is -3i plus 8j. That one was pretty easy. Okay. Now the B part says B is to take twice that u in this form minus 3 times the v, this v, in that form, and see what we get. And again, we just distribute the coefficients across the vectors. That would be a -6i plus 16j minus 6i plus 3j. And then combine like unit vectors, you might say, is -6i minus 6i is -12i plus 16j plus 3j is plus 19j. That's it. Pretty easy, pretty straightforward. Any questions? Ask them if you got them. Okay. Now, all right, before we get to that slide, we still have example 6 to do. So let's do example 6 on our whiteboard. Sorry about that. All right, now I've got a little bit of maneuvering around to do, so hang with me. Probably easier to do it by my finger. Okay, let's move this taskbar that you can't see to the right and upward as far as we can. Okay, and then we'll move the whiteboard, which just looks white to you, but to me it takes up just part of my screen. I'm going to move it as far to the left as I can and as far up as I can to give me the maximum. I'm sorry about my throat. For some reason I've started coughing. Okay. Nowadays that's a scary proposition, isn't it? It shouldn't be, but it seems like it is. All right. Here's example 6. The vector V has a magnitude of 3. This is how I express that in math speak. Magnitude of V is 3 and makes an angle of 30 degrees or pi 6 with the positive x-axis. So let's draw us an axis here. Pretty ugly looking axis. Okay, 30 degrees here would be something about like that. Okay, so we'll call that 30 degrees or pi 6. Pi 6 radian, 30 degrees in degrees, with the positive x-axis. Says write V, and this is your vector V, and it has a magnitude of 3. So I'm going to do 1, 2, 3, 1, 2, 3. Okay, so this is going to sit on that arc between those 2 points there. Okay, write V as a linear combination of the unit vectors I and j. Well, if you bring this down here, you know if this is the angle 30, the sine of 30 is 1/2. This has magnitude of 3, so that magnitude is going to be 3 here. So this should, obviously I didn't draw this too well, that should be at 1.5. Okay, because the y component, let's call it v sub y, is equal to the magnitude of v times this. This drives me nuts. Times the sine of, I'll put 30 degrees. Pi halves is a little harder to write. Whereas the x component, v sub x, is the magnitude of v times the cosine, the adjacent side. That's the x side of 30 degrees. And we know that to be, this will be 3 times, and the cosine of 30 is the square root of 3 over 2, and the sine of 30 is 1/2, so that's 3 times 1/2. Okay, so this vector v then can be represented as 3 root 3 over 2 I plus 3/2 j. Okay. 3 root 3 over 2i plus 3/2 j. And it's a pretty simple thing to go back and verify its magnitude is 3, because if you take the square root of 3/2, that would be squared, would be 9/4 times 3, because the square root of 3 times square root of 3 is 3, plus 9/4. So this would be the square root of, is that my phone? Goodness gracious. I'm sorry, I'm going to have to pause a minute. We live in an old house. Old houses have plumbing problems. I've got everybody here now. Jemanuel, if you're wondering what in the world is going on here, we live in an older house built in 1930, 29 and 30, so it's now 90 years old. Okay, even older than I am, believe it or not. And it's of course, old houses have problems, and this has we're having a plumbing problem now. That a couple weeks ago the guy came and thought we got it fixed, and then at the end of last week and again this morning it's backed up again. So he's coming back, but he didn't have I thought he had all the information, but he didn't, so he was calling back to get our address and home phone number. I don't know why he needs a home phone number, but anyway, he's on his way. Well, no, he's working on another job, and he'll be here at some point. So if and when he gets here, he's going to give me a call. I've got to go downstairs and make sure he's able to come in. We do have a dog. She loves people, but she may get scared of him and bark like crazy and scare him then. So she's not very much of a good guard dog. She's quite a good watchdog, but not a good guard dog. She just watches everything that's going on. So Jemanuel, we're in chapter 11, vectors and the geometry of space. We're in section 11.1, vectors in the plane, and we're doing example 6 at the bottom of page 757. And I was just verifying, we've finished the problem, that this has a magnitude of 3. If I can do this, that would be 27/4 plus 9/4, and that would be, of course, the square root of 36/4, and 36/4, of course, is 9, so square root of 9, and that is indeed 3. You always use for magnitude positive square root. Okay. So sure enough, this works out correctly. And that's what they had in the book. Good for them too. Any questions on that? All right. let's move then back to the PowerPoint. And we'll go back from the slideshow. And we just finished example 5 before we did example 6. And here we're at the top of page 758. Vectors have many applications in physics and engineering. I'll give you several, okay? Displacement is a vector quantity. Distance is not. Distance is the magnitude of displacement, okay? But displacement is how far you moved in what direction. When I used to go to work in Bessemer, I would leave Birmingham and go to Bessemer. Basically, my displacement was approximately 20 miles to the southwest. Not just 20 miles anywhere. That could have taken me up to Gardendale or anywhere. This was to the southwest. That landed me in Bessemer. So a distance isn't going to tell you enough. You need a distance with a direction. Velocity is a vector force. Speed is not. Speed is a scalar force. How fast did I drive? Well, I may have averaged 65 miles an hour or something like that. Well, that doesn't tell me where I was going. My velocity would have been an average of 65 miles per hour to the southwest, again, with a direction associated with it. Acceleration is basically always a vector quantity. It doesn't have a corresponding. A lot of times we'll talk about the magnitude of acceleration, which would be a scalar quantity, but accelerations are vectors. Therefore, a force is a vector, because if you remember from Newton's second law, force is equal to mass, which is a scalar quantity, times acceleration, which is a vector quantity. Now again, we'll often talk about the magnitude of a force, which would be the length of that force vector, but the force is a vector. Momentum is a vector quantity. That's the mass times velocity, but velocity, remember, is a vector quantity. Torque is a vector quantity. There's various other examples of things that are vector quantities. A vector can be used to represent a force because force has both magnitude and direction. Now, if two or more forces are acting on a single object, then the resultant force on the object is the vector sum of the two forces, not the sum of the magnitudes, the vector sum of the two forces, the vector forces. Okay, and here's example 7. Two tugboats are pushing an ocean liner, as shown in this figure here. Each boat is exerting a force of 400 pounds, but the 400 pounds is in the direction that they're pointing. So that is represented by there's a 400 pounds and there's a 400 pound force. Okay? Now, what is the resultant force on the ocean liner? Well, they show here this is 20 degrees below the horizontal here, 20 degrees above the horizontal here. So that means that the resultant force on the ocean liner is the vector sum of these two forces, F1 and F2. Now what they didn't show specifically here is the, well, let's just proceed. Okay, now the force in the horizontal direction here, that's the only force pushing on the ocean liner. The vertical component of the force is not exerting any influence on the ocean liner at all. Same thing down here, is only the horizontal component of this force 1 is pushing on that. The vertical component, get out of there. The vertical component here would not be contributing anything to changing the velocity of the, or to adding to the force on the ocean liner. Okay, now, I do not know why they, oh, I think I see. Okay. I was trying to think why they put sine here. They're talking this is a sine. Okay. Notice the force here, the vertical component of the force, the way this is drawn here, is a minus 400 times the sine of, well, they say of the sine of minus 20, but the sine of minus 20 is minus the sine of 20. So that would be a minus 400 times the sine of 20. This would be a plus 400 times the sine of 20. And that means these two cancel out. There is no net force in the y direction. What are they in the x direction? Well, this is 400 times the cosine of negative 20, if you wanted to call it that, and 400 times the cosine of negative 20, of positive 20 here. Well, the cosine of a negative angle is the same as the cosine of this positive angle. So this is 400 cosine 20 plus 400 cosine 20. So that would be 400 times, well, let's just make it 800 times the cosine of 20 degrees. And there you'll have to pull up your handy dandy calculator to find out what that is. Okay. Okay. All right. Now I've got to turn my phone sideways to get it into scientific notation form, because that's where you have this. So let's just do the 20 degrees first. I need to get in degree mode. Now I don't know where the camera is. I can't tell looking at the thing because I don't have my own picture on here. But wherever it is, you see this up here says radian, and we don't want radian mode. We want degree mode. So down here there's a little DEG symbol. So I'm going to press that and the radian disappears. That means we're in degrees. Okay, when I want to go back to radians, I hit there because that changed to radian. So let's do 20 degrees and take the cosine of it and multiply that by 800. And that gives you 752 pounds approximately. So this would be approximately 752 pounds. Now frankly, just between you, me, and the sidewalk here, that's not a lot of force. It doesn't seem like to me to be pushing on the ocean liner. But remember, it's in water and you probably are wanting to move it pretty slowly, so that probably will move it, albeit very, very slowly. Okay, now that was, I just gave the magnitude, but remember this is in the x direction, so the proper way to do that force, the net force, I'm just going to, they don't call it net force, but I'm going to call it net force, is equal to 752 I. Okay, and that would be in units of pounds. Whoa, here comes James. Let me let James in here. Finally, well, no, I think what's happened now, if I remember my roll book well, yep, we got all four people in the bottom part of the alphabet here, and the top part is still being held down by Kira alone. Let me make sure nobody else is waiting. I thought for sure, oops, I can't. Esther was going to be here today because she said she finally got Blackboard. Oops, that's the wrong slide. Okay, this is the one I want. Yep, that's it. 1, 2, 3, 4, 5. Got it. Okay. All right. So what is the resultant force on the ocean liner? 752 pounds in the positive I direction. Okay. I was going to write, oh yeah, I was going to write my units there in pounds. If I can find my pen. Well, wrong end of the pen. There we go. There we go. 752 pounds in the positive I direction. Okay. Now, let's watch how they did it. They use pluses and minuses and stuff like this, which is fine. It's probably more correct to do it that way, but you can just look at the figure and tell. Using figure 1112, which I was using, you can represent the forces exerted by the first and second tugboats as the first tugboat was the one on the bottom, remember, 400 times the cosine of 20 degrees in the positive x direction, sine of 20 degrees. Here comes Esther. Good deal. Okay. Good to have Esther back again. And it also helps Kara hold down the fort in the top part of the alphabet. And also, now we can say 100% of the X chromosomes are here, and not all the Y chromosomes are here. So we can phrase it that way as well. So welcome, Esther. Okay. We're in chapter 11, Vectors in the Geometry of Space, section 11.1, Vectors in the Plane, and we're just wrapping up example 7 at the top of page 758. And here is the figure. If I could get it to advance or retreat, it won't do anything. Here we have two tugboats pushing on an ocean liner. This one's at 20 degrees below horizontal. This is 20 degrees above horizontal. Okay, I've already done my marks on it. Here's how they're doing it. The vector sum of the force 1, that's the one down here, the one pushing this way, is the magnitude of F1, 400, times the cosine of 20 degrees in the I direction, sine of 20 degrees in the J direction. So we did 400 times cosine 20 degrees written in component notation, comma, sine 20 degrees here. The magnitude multiplies each, but it's easier to keep it on the outside. F2 on the other, and that's written as 400 cosine 20I plus 400 sine 20J. Now the reason they went to IJ notation, they make it seem like it's going to be easier to work with. It would have been just as easy to stay in component notation. I don't know why they changed, but they did. All right. So, whoa, wrong way. Okay. The F sub 2 is 400 times cosine of minus 20, that's in the I direction, and cosine of and sine of minus 20 in the Y direction. But cosine of minus 20 is the same as cosine of 20, whereas sine of minus 20 is minus the sine of 20. So they went back and did this. If they had just put a plus here and a minus in front of sine and a plus there, that would have been just as good left in component notation. But they choosing to do it this way, it's fine. Now you add the components together. F1 plus F2. So that's 400 cosine 20I plus 400 cosine 20I here, plus 400 sine 20J here, minus 400 sine 20J here. These two obviously add to 0. These two add to be 800 times the cosine of 20 degrees I. And that's what they got there. And then multiplying 800 times the cosine of 20 degrees, you get approximately 752 I. Now, I think they should have the term pounds after it. Maybe they're going to do that. Excuse me just a second. I've been talking all morning, so my voice is sort of scratchy. Hopefully that'll help a little bit. So the resultant force on the ocean liner is approximately 752 pounds in the direction of the positive x-axis, which most of the time we assume is due east. They didn't say that, but we'll make that assumption. Which then leads to, if we advance the slide once, in surveying and navigation, a bearing is a direction that measures the acute angle that a path or a line of sight makes with a fixed north-south line. In air navigation, bearings are measured in degrees clockwise from north. Okay, and whoa, that's all. That's it, folks. Okay. I don't know why they specify that. I believe it's also in surveying as well. But anyway, let's do example 8 then. I think we will need this whiteboard, so let's go back to the whiteboard. Any questions so far? I'm going to clear this unless you don't need that any longer. And by the way, example 8, you can also see larsoncalculus.com for an interactive version of this type of example. An airplane is traveling at a fixed altitude with negligible wind factor. The airplane is traveling at a speed of 500 miles per hour with a bearing of 330 degrees. Okay. Now, they're almost contradicting what they said. They give you the bearing in degrees, and they're not doing a, as I said before, an acute angle. Okay, they're doing the total angle from due north, 330 degrees, which is 30 degrees short of coming back in again. So let me see if I can draw, and I don't draw my axes too well. That's supposed to be a straight vertical line, which obviously it's not, and this should be a straight horizontal line, which obviously it's not. Okay, now 330 degrees from due north, this is going to be due north now, so this would be 90, 270, 90, 180, 270, and to get to 330, you're going to be, this drives me nuts. It won't draw. It just changes to, here it did it again. Why it won't draw, I don't know. Okay, now obviously I didn't do that. I was trying to do it fast before it shut it down again. We're going to call this 330 degrees from due north. That's the bearing, which means this left is 30 degrees here. And obviously my drawing isn't quite accurate. Okay, and he's going at a speed, so let this be his velocity vector, the magnitude of which is 500 miles per hour. Okay. As the airplane reaches a certain point, it encounters a wind with a velocity in 70 miles per hour in the direction north 45 east. Now what does that mean? The wind north 45 east, that means if you set up another little axis up here, then that would be, this is again north, this would be east, and that would be 45 degrees east of north. Okay, 45 degrees east of north. That's going to be a wind, and this is going to be the magnitude of 70 miles per hour. My pen is really doing strange things today. Okay? Now, they have a picture in the book. Please look at the picture in the book. Okay, it's a lot better than mine. It says, what are the resulting speed and direction of the aircraft? Okay, speed and direction. Speed is the magnitude of velocity. So what we've got to do is find out what the velocity is. Okay, and the velocity vector will be, ooh, this is ugly. Something about like this. If my drawing is anything close to accurate, which it's not, it would be something like this. Okay. Okay. This would be the new velocity vector. Okay. Now, here's the issue. None of the angles up here are 90 degrees, or you're certainly not guaranteed that they are, and they're not. They just are not. So what you're going to have to do is break this down into components. Okay, so the new velocity vector here, let's call it V, is going to be the component of the plane's velocity here, which is going to be 500, and the x component here is going to be the cosine of 30 degrees. I hope you see that. If that's 30 degrees, 500 times the cosine of 30 would be this here, and that's going to be a negative 500 cosine 30. Okay, plus its vertical component is going to be 500 times the sine of 30. Now, I don't think I'm saying this correctly. No, I've got them backwards. Okay. Okay, because we're not doing from the x-axis anymore, we're going from due north. Okay, so the x component here, I can't see, yeah, there it is. Here's the x component of that original one. The opposite here is the x component. So this is going to be the sine of 30 degrees, and this is going to be the cosine, because the vertical component of that is going to be the adjacent of 30 degrees. So that is the initial velocity of the plane. Okay, now the wind velocity, I'll call that V sub W. Okay, maybe I should call it W, I don't know, it's easier to see. Okay, and again it's the same type deal, only both of those are positive in x and positive in y, 45 degrees, so that's going to be 70 times the sine of 45 degrees plus 70 times the cosine of 45 degrees. Okay, now we know what all those things are, so let's write them down from our knowledge. 30 degrees, the sine of 30 is 1/2, so that's going to be minus 250. I forgot to put my i's and j's in here. This is in the I direction, this is in the j direction, this is in the I direction, and this is in the j direction. Okay, so that minus 250 miles per hour in the I direction plus 250 times root 3, because remember cosine of 30 is square root of 3 over 2, so the 2 divides into that, and then you multiply that, and this is in the j direction. And the wind speed is 35, because it's sine of 45 is root 2 over 2, so dividing by 2, 35 root 2 I plus 35 root 2 J. Okay, so we add these together and we get a minus 215. Whoops, I forgot the root 2. Sorry about that. I keep forgetting which eraser I use on this slide. It's the one up here. Okay, so it's minus 250 plus 35 root T I plus 250 root 3 plus 35 root 2. I left off my 5, didn't I? And this will be J. Okay, now I think it's time for a calculator because I can't do much of this in my brain here. So this is going to be approximately get my calculator in scientific mode. I'm going to do the 35 times root 2 equal, and then subtract from that 250. And that gives me a minus 200.5. Let's just round it to that. Minus 200.5 in the I direction, plus, and now that'll be a 250, if I can read my writing, 250 times root 3 plus 35 times root 2 equal, I get 482.51. 482.51 J. Okay. Now, what do we got to do to get the magnitude? The magnitude has got to be the square root of the sum of those squares. Okay? So let's do, I'm going to use the one on my screen now and square it, plus 200.5, and I don't have to worry about the minus sign because when you square it, that disappears, and that gives me an equal, and then take a square root of that. There we go. So I get a resultant speed of about 522.5. Goodness gracious, I can't get this thing to write. Miles per hour. Now, does that sort of make sense? Yeah, the plane was going at 500 miles per hour this way. The wind was blowing it this way, which was basically somewhat of a tailwind. Also off the quarter, but still a tailwind, so that should have increased it a little bit, and it did. So 522.5 miles per hour is the magnitude. That answers the first part. What was the resultant speed? Now the question is, what is the final direction of that aircraft? Okay, Now here's what we've got to do there. If you think about it now, it's component here and it has a very small component here. We've got to add those two components together. Okay. Oh, here they are, added together for us. Okay. Now, the tangent of the angle that's resulting here is the y over x. Okay. So we know that the tangent of the angle theta that we're looking for, this will be the resultant angle, is going to be 482.51 divided by a negative 200.5. Okay, so let's see what that gives us. 480. I have fat fingers and little bitty keys here, so I don't do too well on this phone. 482.51 divided by 200.5, and that's you negate that one, and that gives you a tangent of theta is equal to negative 2.4. Okay, approximately. Okay, now I want to take the inverse tangent of that. Now, to do inverse on your phone, you have to go to the second key, which is one up here, and that changes the sines and tangent, cosine and tangent, to inverse sines, cosines, and tangent. So I'll take the inverse of that, and that gives me 67 degrees. So theta, I'm just going to call that R still, it's not the angle I'm looking for, is negative 67.4. Let's just leave it like that, degrees. Okay, now we're in degree mode. Now something doesn't feel right about that, because this should be a smaller angle than what we had before. But you see, it's a negative angle, so you're going to have to add 180 to that to get the positive of the angle that we're looking for. So add 180 to that. I believe that's right. Let's see what happens. Plus 180. Okay. And that would be, there's something that's not doing right here. Oh, I did it again. Okay, I'm thinking in terms of the x-axis. It's not. This is, remember, here going from due north here, this is your the I component is your adjacent component, and the x is your opposite component. Okay, because the y that you're measuring here, this is adjacent to your angle that you're dealing with here. So again, I'm doing it backwards, so I need to put the tangent, and let me go back. I knew that didn't feel right. And why is this not erasing? There, I didn't have my button pushed. Okay, you have to remember your sine, the tangent is sine over cosine, and you remember your sine was your no, that's not what I want. That's what I want. Okay. Okay. when you're going due north, the X component here is your adjacent side, and this is your opposite side here. The vertical component is the opposite. I said that backwards. The I is the opposite side, and your J is the adjacent side. So therefore it's opposite over adjacent, so it's minus 200. Oh, here comes James. Well, James must have had to bounce out and come back in. I wish I could get him. There we go. If I hold my pen too close to the Wacom, I can't get it to move. Yeah, we already had James here. Okay. This is negative 200.5 over 482.51. Okay, so let's do that. 200.5. I'll go on and put the negative in there, but don't let it throw you. Divided by 482.51, and that's a negative 0.415 and so on, and then take the arctangent of that, inverse tangent of that, and we get, this sounds better, about 22 degrees and 0.56. Let's do 22.6 degrees. Now they say negative, meaning it's on the left hand side of your that, so if you gave that in terms of a bearing, you'd add that to 360. So add to that 360. Again, my fat fingers on these little keys doesn't work well. And that gave me a totally bizarre answer. It was 22.6 negated plus 360 equal 337.4. So the bearing was, the actual bearing of his flight, I wish I could find, there it is 337, let's just leave it at 337 degrees at 522 point something another miles per hour. Let's see what we got here. And now they go from the positive x-axis, which I don't know why they do that. If the problem was given with a bearing, the answer should be given with a bearing. Okay? And yet they do it from the positive x-axis. And if you did that, the number we had before was right, the 112 degrees, and I don't think that's right either. Oh, okay. Yeah. They didn't go around here. They went from positive in this direction. Okay. And if you add 90 degrees to that, that's what you get. Wow, what a weird way to do this. Yuck. For some reason my calculator is getting very weak. My phone is, okay. So what do we have? Minus 22.6. Okay. And add to that 90 degrees. 112.6. So they did do it right. based on from the positive x-axis. Now why they moved to that, I don't know. In my mind they should have left it this way, which was, what was it, 22.6. I would have said 22.6, lose the sign here and say north 22.6 west. That would have given the correct thing. So I don't know why they flipped back and started doing it from the positive x-axis again. Nothing in the problem had been from the positive x-axis. But don't sweat that too much. It's sort of like they threw it in there anyway. Well, that finishes 11.1. Concept check, always a good thing to look at, think through, make sure you understand, and then start working on your homework exercises. Number 3 is at Calc Chat and 5 and 7 are at Calc Chat, 5's at Calc View. Any of the odds 9 through 15 are at Calc Chat, 11's at Calc View, 17's at Calc Chat, 19 through 23 are at Calc Chat with 21 at Calc View, 25's at Calc Chat, 27's at Calc Chat and Calc View. Any of the odds 29 to 33, they're all at Calc Chat. 35 or 37 are at Calc Chat, 35's at Calc View. 39 or 41 are at Calc Chat, and 43's at Calc Chat. 45 and 47 are both at Calc Chat with 47 at Calc View. 49 and 51 are at Calc Chat with 49 at Calc View. 53 and 55 are at Calc Chat. 57 and 59 are at Calc Chat. You can explore doing those. 61 through 65 are at Calc Chat. 67 through 71 are at Calc Chat. 73 is at Calc Chat. 75 or 77 is at Calc Chat. 79 is at Calc Chat. And any of the either 81 or 83 are at Calc Chat. Okay. There's true false, 85 through 93 are at Calc Chat, and 95 through 99 are at Calc Chat. Okay. Any questions? All right, let's then exit here. Let me go back to my PowerPoints. Okay, and I'm going to exit there and exit here and pull up this one. Okay, I'll get screen share back in a minute, but it moved it back up here. What a pain in the neck this is. 11.2. And let me move this taskbar back down. Have to do this every time. And we will go from current slide. All right. Chapter 11 again is vectors in the geometry of space. 11.1 was vectors in the plane. 11.2 will be space coordinates and vectors in space. So now we're moving from two-dimensional plane geometry, you might say, to three-dimensional spatial geometry. So we'll be talking about spatial coordinates. You can't get by with 2 coordinates now. You've got to have 3. X, Y, and Z. Okay? 3-dimensional space. And we'll be talking about vectors that have 3 components, not just 2 components. Okay? The objectives here: understand the 3-dimensional rectangular coordinate system and analyze vectors in space. So let's first talk about coordinates in space. Before extending the concept of a vector to 3 dimensions, let's first identify points in a 3-dimensional coordinate system. Now here's a problem, folks. The only way I can draw these, and the book can draw them, is on a 2-dimensional screen, okay? Yet we're trying to draw three-dimensional points on there, and it's really hard to do and distinguish. So you have to let your mind do some third dimension for you. You can construct this system by passing the z-axis perpendicular to both the x and the y-axis. X coming this way, y going that way, z going up. Okay, so here's the x in this direction. Now this is supposed to be the horizontal plane here, and this is the y in this direction. So the xy plane is your floor, the horizontal plane there. Then z moves upward. That's the corner of the wall from the floor. That's your z component. Now, as I said before, the floor here is the xy component. This wall over here is a yz plane, and the wall over here is an xz plane. Say the wall back here is the xz plane, the wall over there is the yz plane. Okay, and the floor is the xy plane. Okay. Taken as pairs, the axes determine three coordinate planes, which were just described. Okay. Now, something about the x, y, and z. You have to draw these. Excuse me, just a second. My throat's going on me. Didn't have much left of that. The XYZ coordinate system has to be a right-handed system. In other words, if you point your fingers in the direction of the x-axis, curl them of the right hand in the direction of the y-axis, your right thumb is pointing in a positive z direction. Okay, so x is pointing in the positive, your fingers are pointing of your right hand pointed in the direction of the positive x-axis. Bend them so they're pointing in the direction of the positive y-axis. Your right thumb is then pointing in the positive z direction. These three coordinate planes separate tree space into 8 octants. Now we number our quadrants 1, 2, 3, and 4. I've never heard how they number the octants. Okay, they'll always refer to this one, positive x, positive y, and positive z, as the first octant. That's above the floor and inside the corner of the YZ plane and the XZ plane. They'll always call that the first octant, but I don't know where you go from there and where you go up or down, right or left. I don't know where you go. They never number those 8. They just say there are 8 of them. The one where you have positive x, positive y, and positive z, they usually call the first octant. Okay, the numbering is not nearly as important as it was in the plane. Okay, the first octant is the one for which all 3 coordinates are positive. In this three-dimensional system, a point P in space is determined not by an ordered pair, by an ordered triplet. X, Y, and Z. You've got to give a component for each, where X, Y, and Z are as follows. X is the directed distance from the YZ plane to point P. Y is the directed distance from the XZ plane to point P, and Z is the directed distance from the XY plane, the floor, to the point P. Okay, so here's a few points shown. This one is positive 3 on the X, positive 3 on the Y, but going down 2 on the Z. Okay, this one over here is going positive 1 on the X, positive 6 on the Y, 0 on the Z. Okay, here we're going negative 2 on the X, positive 2.5 on the Y. Wait a minute. Oh, they've really messed this up. The X scale, they listed every point. ticked off every point. The Z scale, they ticked off every point. On the Y scale, they did every other point. 2, 4, 6, 8. -2, -4, -6, and -8. Where here they did every one. Okay. So why they did that, I'm not sure. So you're going -2 on the X, +2, 4, 5 on the Y, and +4 on the Z. Now, that's a bit strange in the fact, well, this 4 seems to be higher than that 4 is, but that's because you're relative to a plane that is somewhat elevated in the back. Okay, let's go to this last one. +2 on X, -5 on Y, and +3 on Z. Okay. Now, it looks like to me, oh, and it is, you're somewhat elevated there. It's really hard to picture these points well because they're drawn on a two-dimensional plane, but they're trying to be representing three-dimensional space. Okay, so there's that representation. And as long as you draw the dotted lines in there, it makes sense. If you just took them off and put a point there, you don't know if it's a point that's back here or up here. I mean, it's hard to say because without those dotted lines, it's hard to say where in the space that point is because you're drawing it on a plane. Okay. Now here's what we're talking about. Our three-dimensional coordinate system can have either a right-handed or a left-handed orientation. No one, hardly at all, ever uses a left-hand orientation. Why do they even bring it up? You usually use the right-hand rule. And to determine the orientation of that system, imagine you're standing at the origin, your arms pointing in the direction of positive X and positive Y. Then if your right arm is pointing in positive X, your left arm in positive Y, the positive Z is directly up. That is a right-handed system. A left-handed system depends on which hand points in the positive X direction. If you pointed your left hand in positive X and right hand in positive Y, then Z would be going up. So it's wherever you choose that first hand to go, which direction that would be, whether it's right or left. So right hand positive X. If left hand is in positive X, then it's a left-handed rule. No one uses the left-handed rule. Why did they even bring it up? I don't know. Many of the formulas established for two-dimensional coordinate systems can be extended. I'm breaking up. Sorry again, let me get some water this time. Can be extended to 3 dimensions. For instance, the distance formula, distance between any 2 points in space, use the Pythagorean theorem twice. Okay, so from point P to point Q, you go your x1, not very far here, y1, that would be this one, y1 to y2. See, I can't tell where the first point is here. Is that on the YZ plane or where? They're just hanging it up there. X1, Y1, Z1. Somewhere there. Without those dotted lines, it's hard to say where that is. Okay? And you're going to this point here, so your change of X's is from this X to this X. Okay, and it's not a lot of change here. It looks like this X is on the negative side of the X-axis. This is on the positive, but not very much. So anyway, the difference in those X's, x2 minus x1 squared, and then your y2 minus y1 squared, that would give you, yuck. for the life of me, I do not see where they've indicated that here. Yuck. That is in here somewhere. Here's your Y2 here. Here's your Y1 back here. So that's a very small difference there. I guess that would be this distance here. Y2 minus Y1. Yeah. Y2 minus Y1. That would be that distance there. So the X2 minus X1 would be here. Y2 minus Y1 there. So this would be the vector sum of those two, okay, squared of course, would be the length there, and then combine that with the Z2 minus Z1 here, and that gives you your total distance. Now that figure and all the things else leave a lot to be desired, but here's, by doing that, you obtain the formula for the distance between the 2 points, x1, y1, z1, x2, y2, z2. They should have just gone straight here. Square root, just like before, of x2 minus x1 squared plus y2 minus y1 squared. Now you add to it a plus z2 minus z1 squared. Square root of all that summed together. This is always positive, that's always positive, that's always positive, or non-negative at least. And so when you add the three together, it's going to be non-negative, and then take a square root, and that will of course be positive. So let's find the distance between these 2 points. Now, frankly folks, it doesn't matter which one you count as 1 and which one you count as 2. Doesn't matter at all, but you just got to be consistent. Okay, so the distance between will be the square root of, now I'm just going to start with this one, called this 2 and that 1. So 2 minus 1 would be 1 squared, plus, always pluses in between, negative 1 minus 0 is a negative 1 squared, and 3 minus a minus 2 is plus 5 squared. And if you'd have done it the other way, it would have still come out the same thing. Okay, and this would be the square root of 27, which would be 3 root 3. Okay, now that's how I did it fairly rapidly. Let's see how they did it. Okay, they chose and did it the other way, so they had a minus 1 squared, plus 1 squared, minus 5 squared. But guess what? It comes out the same thing. 1 plus 1 plus 25, which is the square root of 27. Let's see if they break. Yep, 3 root 3. They took it all the way down. Good deal. Any questions on that? Really easy to determine distance between 2 points. All right, let's move on to another concept here, and this is just below example 1 on page 763. Now, how are we doing on time? Okay, we got some time here. Okay, a sphere with a center at x0, y0, z0, just some point out here, not the origin. Radius r is defined to be a set of all points x, y, z such that the distance between x, y, and z, any point on the sphere, and that center is always r. Now you can use the distance formula to find the standard equation of a sphere of radius r centered at x0, y0, z0. Okay? Because you know the r is the distance between those 2 points. So basically that says that r is equal to the square root of x minus x0 squared plus y minus y0 squared plus z minus z0 squared. Square root of all that entity there. And then what you basically do is square both sides and you get x minus x0 squared plus y minus y0 squared. I don't know why it did that. Plus z minus z0 squared is equal to r squared. Okay? And another way you could write that would be x minus x0 over r. I think I like it better like this. Squared over r squared plus y minus y0 squared over square over r, getting the scratches, squared plus z minus z0 squared over r squared is equal to r squared. Yeah, oh no, is equal to 1. I've divided everything on both sides by 1. That to me is a standard equation for a sphere of radius r centered at x0, y0, and z0. I think they may list it like this. They are exactly equivalent. This though is a more standard. Let's see which one they listed as. They do that exactly like that, but they left it in that form. I like to divide both sides by r squared, and that to me is the better standard definition. But there's your sphere up there with the center x0, y0, z0, and then the x, y, z is one radius from that center anywhere on there. Moreover, the midpoint of a line segment joining points x1, y1, z1 with x2, y2, z2 has coordinates. Add the two x coordinates together, take the average of the x coordinates, comma, average of the y coordinates, comma, average of the z coordinates. That's it. That's the midpoint formula. Okay? And I just can't think of many circumstances where I need that, but there it is. Okay. Now let's see. They're skipping example 2, so let's go back and do example 2 if we have time. We probably do. Let's try it because it's a pretty simple example, I think. So let's go to the whiteboard. It says find the standard equation for a sphere that has points as the endpoints of diameter. Okay, so they are going, okay. Now I thought this was going to stay the same, it didn't, so I'm going to have to move this again. And this one stayed okay. Alright, so let's clear our writing here. Now, find the standard equation of a sphere that has the points 5, negative 2, 3, and 0, 4, negative 3, as the endpoints of a diameter. Okay? Well, if those are the endpoints of a diameter, then the center has to be the center of that diameter. The center of the circle would be that. So what would that be? That would be, the center would be half of 5, which is be 5 halves, comma, add these two together, you get 2, half of that is 1, comma, add these two together, you get a 0, and half of that is 0. So there's the center of the circle. Okay, now 5 has 1, 0, exactly. Now, what is the radius of that? Well, the radius of that would be exactly half the diameter. So we have to figure the diameter first. The diameter is the distance between these two. So this is going to be diameter. That's what the D stands for there, is the square root of 5 squared. That's the difference in those two. Negative 6 plus a negative 6 squared plus 0. Okay, that one's going to be 0. We know that one. No. Difference between those two would be a negative 6 squared. Okay, sorry about that. I'm in a hurry because we're running out of time. This will be the square root of 25 plus 36 plus 36, and this would be the square root of 72 and 25 would be 97. Okay, so that's your diameter and half of that is your radius. Okay, let me make sure I did that right because So if you want the radius squared, you just square that. So what we have, your equation of a circle, of a sphere, is going to be, and I'll write it in the way they want to, okay, x minus 5 halves squared plus y minus 1 squared plus z squared, because that's minus 0, is equal to the square of this, which will be 97 fourths. That's probably how they will list their answer. Let's see, x minus 5 halves squared plus y minus 1 squared plus z squared is equal to 97 fourths. Perfect. That one I think is better in that form. If you divide it by that r squared, that would be a messy looking thing, so leave it in that form. Okay. Well, we got 4 minutes left. 3 minutes left. I didn't think we'd get through it that quickly, but we did. That was a fairly easy problem. Now let's go back to our PowerPoint. Okay, and that used the midpoint formula because they gave you the endpoints of a diameter, so the midpoint is going to be the center, and then we use this form to get the equation for the sphere. Alright, vectors in space. Okay, 3 minutes. Let's see what we can do in 3 minutes. In space, vectors are denoted by ordered triples, v being v1, v2, v3. This is in vector component notation. The 0 vector is the bold 0, the only one that's not a lowercase alphabetical letter. This is the 0 bolded, or with 0 with a bar arrow over it, is 0, 0, 0. Those are the 3 components. Using the unit vectors I being 1, 0, 0, j being 0, 1, 0, and k, introducing k here, 0, 0, 1 as the standard unit vectors for any vector v, we can take what was our component notation and do v sub 1i plus v sub 2k is j plus v sub 3k, and that's it. So here's a vector. Here's your unit vector I, j, and k. And this would be, it looks like maybe about 2i in this direction, looks like maybe 1.5j in this direction, and then I don't know, maybe about 3k up here, whatever it happens to be. That would be whatever this component is in the I direction, v1, v2, v3. Now the v3 is the distance from here to here, which would have gone on up here somewhere because of that foreshortening that you have there. Okay. Now, one more minute. If V is represented by the directed line segment from P, P1, P2, and P3 to Q, Q1, Q2, and Q3 as shown in the figure, then the component form of V is written just like before, subtracting always the initial from the final. So that would be Q1 minus P1, Q2 minus P2, Q3 minus P3. That makes up your components V1, V2, and V3. Just like we did in 2 dimension, extend that to 3. Alright, vectors in space. Well, let's see if we can get these done. Well, I don't think we can. Not adequately. So we will begin there next time. Vectors in space, the block right there, and let me get my marker in place, and let's see what you can do as homework. You can do any of the odds, either 5 or 7, so they should both be at Calc Chat. 9 or 11, they should both be at Calc Chat. 9's at Calc View. And I think you can do any of the odds 13 through 23. Those inequalities might give you a little bit of an issue there, but I don't know that we're going to be doing them any other place, so try to do those. Distance between 2 points, you should be able to do 25 or 27. They're both at Calc Chat. 25's at Calc View. And classifying a triangle. Try those, 29 or 31. You'll have to read that and see what they're talking about. And then you should be able to do 33 or 35, both at Calc Chat. 33's at Calc View. And any of the odds 37 to 41, they're all at Calc Chat. 39's at Calc View. 43 or 45, they're both at Calc Chat. And I think you can do 47. It should be at Calc Chat. I think you can do 49. It should be at Calc Chat. 51 or 53 should both be at Calc Chat. 51's at Calc View. 55 should be at Calc Chat. Let's see. Maybe hold off the rest of those. We'll do those after we do the vectors in space here. Okay? Any questions? All right. This is a pretty short section, so we're going to finish it pretty quickly and move on to 11.3, which is something you may have done before, but we'll see. So I'm going to stop sharing unless I hear any other issues and any questions before I end the recording. So we were only missing Houston and Kyle today. So sorry we missed them, but we'll end the session here and we'll see some of you in about 30 minutes and the rest of you will see on Wednesday. I'll see the same 3 again tomorrow, or 3 of you tomorrow. Okay. I'll see all of you on Wednesday. Take care. Any questions? Bye-bye.